video, we're going to be talking about discrete time signal and in particular topics which are impulse response and convolution. First of all, we want to say a brief definition of impulse response. Impulse response is typically the response of a system y of n when the input x of n is an impulse function. And usually, as we have here in this photo, the input n is the unit impulse when it enters a system or like an LTI system. It gives us the output of h of n, which is the impulse response or the unit impulse response. And we want to talk about how this impulse response in terms of why is it important as in signal processing. The impulse response of a system or signal is usually like the output that results from applying a brief input signal. And this could be known in other words as impulse function to the system or the signal. And if we say we have an input and this is the box, which is our system, it's gonna give us the output, which is gonna be h of n, which is the impulse response. And with the impulse response, we can analyze the pattern of the input x of n to the output y of n. And this could be easier by just applying the impulse. And for example, as we are seeing here, this black box, it produces a signal that we don't know how the output is created. Applying the impulse, we can easily determine the pattern of the black box. And if we want to go further in this, like the definition of discrete time signals, when the impulse function is applied to a system, it produces an impulse response, which can be shaped as this particular shape in the graph. And this impulse response of the system, it usually describes how the system responds to the input signal given to it. And as we often use the impulse response to characterize the behavior of a system or signal, and we can use this in many systems as an audio system or even a digital system. And right here we have an example, and we want to find the impulse response of the given for this particular example. So we can start as we're given y of n equals half x of n plus half x of n minus 1, and we can let h2 of n denote the impulse response. Of the length 2. And moving the average filter, we will use a subscript to indicate the length of the video, the length of the window we're trying to get, and this would make it a lot easier to compute h2 of n by setting x of n as a unit impulse to the system. And we can see here by doing this, we can express h2 of n as system unit impulse, and we can equal this to have this signal right here, and that's how we can get a lot easier the impulse response. And here we got the convolution. And convolution can be defined as a mathematical operation that combines two functions to produce a third function that expresses how one of the original functions modifies the other. And in context of signal processing, it's a fundamental operation that can allow us to analyze and process signals in many different ways. And in discrete time signal processing, in particular, convolution can be defined as the following equation and this summary here, as if we are given two discrete time signals x of n and h of n, their convolution is y of n can be computed by this equation right here, which is the summation when k from k equals negative infinity to infinity. And by this, we can get the convolution. And in other words, the convolution of two signals like can be explained as obtaining it by sliding one of the signals, and usually it's like h of n over the other, which is x of n, and then we can multiply like two at each point of the overlap, and summing the products. And then the resulting signal y of n describes how the system represented by h of n modifies the input signal of x of n. And then we have like different methods of solving and getting the convolution of a signal. The one we're discussing now is the graphical method, which can be done in four steps. The first one is we graph both input signal and the transfer signal. Secondly, flip and shift the transfer signal by the value of k, and then we can identify the transition point when we have moved and flipped the transfer signal along with the input signal at the same time. And then we can regraph each transition point and calculate the response to each case. And here we have an example, and we are given like the input signal and the transfer signal of a system with their respective graphs, as we have right here the input signal of x of n expressed as with this expression, and its graph is right here. Oh, I'm sorry. Its graph is this one. And we have the next input signal, which is going to be convoluted with x of n, which is h of n, and it's this one right here. And we will find it useful, I think, to like sketch the functions x of k and like hn minus k as we saw in the previous slide, like the equation. We can get the convolution and we can begin evaluating the convolution result. And we can start now by like seeing how the graphs of each case and how the three different possibilities of the graph like overlap. And we can see here in the next slide for case number one, we have when n is less than 0, we have the signal x of k and hn minus k, and then we have the product graph signal when both of them are like multiplied. And then we have the same case for case number two, which is when n is less than or equal to 0 and less than or equal to 6. And we have the same for case number three, where n is just greater than 6. We're gonna have the following graphs. And you can see how like they are somehow similar to each other, like in terms of like the graph continuity and its shape. And then after that we can start and like try to get how this every case alone works. And we can start by case number one. And case number one is here as when n is less than 0. And when n is less than 0, there is no overlap between the two functions. And in this case, the product equals 0 for all values of k. And we will have output signal. It is gonna be looking as y of n equals 0 for n less than 0. And then for case number 2, when it's when n is less than or equal to 0 and less than or equal to 6. For this case, the two functions overlap, like for the range of the index, setting like the summation limits, and the output signal can be like written as y of n summation and the limits and k equal 1 and k equal to 0. That's 1 and 0.9 and minus k. And with this expression, it can be simplified by factoring out like the common term 0.9 to the power of n, and we can do this, and we're gonna end by the equation of y of n, which can be equal to 0.9 n summation when k equals 0 to n 0.9 k. We're gonna get the result of 0.9 n, and we're gonna have 1 minus 0.9 minus n plus 1 over 1 minus 0.9 minus to the power of minus 1, and thus will give us the final answer as minus 9 0.9 n minus 1 over 0.9, and this is for this particular case. And then we're gonna have like our last case, which is case 3, when n is greater than 6. And for this, we're gonna have the equation of y of n as the following: the summation 1k equals 0 to 6. We're gonna have 1 0.9 and minus k. And again, we can factor out like 0.9 n, this term, and we can get y of n as the final result 9.8168 0.9 n for n greater than 6. And we can summarize all of this in order to get like the final signal and how it looks like as 0 and minus 0.9 n, and those are like our three regions. And the last one is 9.8168 0.9 n, and those are the conditions. And here when it's n greater than 0. And lastly, we can see how when we get the final product of all of the signals, the signal is going to look exactly like this graph after we combine the three different regions. And here in this slide, we have our second method of computing convolution, which is the tabular method. And this method, we classified it here into five necessary steps, and they're very easy to contribute. And the first one is to create a table as the input values is the column order, and the transfer values is the row order. The second step is multiplying the values of the columns with the values of the rows in order to fill out the table. And the third one is to draw a diagonal line across the table from bottom left to upper right. So we can have like a distinguished diagonal line, which will help us determine the rest of the output. And the fourth step is to add values for each line. And the result of each line would be the values for the response we're going to have. And finally, the last step is usually when we're given like the n equals k for input value and the transfer value, we should track the table to see where the result would represent this k value in the response. And here in this next slide, we have an example. We got an input and transfer signal of a system, and we're asked to find the response of the system. So first of all, we need to do our table and do our values, like the upper values of the table will be our x of n inputs, which is negative 3, 7, and 4. And we have our h of n values, which are going to be 4, 3, 2, and 1. And this is x of n, and this here's h of n. And then we're gonna multiply the rows and the columns. So we have negative 3 times 4, it will give us negative 12. 7 times 4 will give us 28. 4 times 4 will give us 16, and so on till we fill out the table. So we're gonna have for this row these results: negative 9, 7 times 3, 21, 4 times 3 is 12. Then we're gonna do the same for the next two rows, which are gonna get 14, then 8, then negative 3, 7, and 4. And then after we have done our table, we got our values, we can do our diagonal lines where they're gonna be in this notation. As you can see, it's gonna be like this. And after we got like these diagonal lines and we computed our table, we now are gonna find the output of our signal, which will be as y of n equals negative 12, as we're gonna multiply, like we're gonna put our results, and we're gonna add like these ones to get the result, and we're gonna add everything to get addition. Okay, so yeah, we're gonna get these values: 13, 19, I'm sorry. Then we're gonna have 31, 23, 15, and 4. And in order to determine, we need to like get the value when n equals 0. And for this particular thing, it's gonna be negative 12. As we see here, when n equals 0, it's negative 3, and when n equals 0, it's 4. And when we multiply these two numbers, we're gonna get negative 12. And this is our value for when n equals 0. And now let's have a quick discussion on how like convolution is different, and like the similarities when it's done in discrete time and continuous time. And we can start with the similarities. As we know, like the definition basically, like it's pretty much the same for both discrete time and continuous time signals. And usually convolution is a mathematical operation, which, as we said earlier, it combines two functions to produce a third function. that should express how the original functions modify the other ones. And also like from the similarity they have the same properties. And yeah, we can, but on the other side, we can see some very clear differences. And the most clear one would be the mathematical notation for convolution for discrete time and continuous time. As in discrete time, in discrete time, we have, we have like the asterisk symbol, but in continuous, we have the integral symbol in order to compute the result of the convolution. We're gonna have we have the integral, and yeah, that's one of like if not the most important difference between like the continuous and discrete time signals and within the convolution computation, as this is a major difference in calculating the results. And we can also see that like the signal representation is somehow different, as discrete time signals are represented as sequences of values, while the continuous time signals are more often like represented as functions of time. And that's it for discrete time convolution.